SwayamPrabha. Digital India. Educated India.
Let us continue discussion on the different issue of the cutting tool breakage. And we have started discussion about the tool runout, and we have seen that tool runout is one of the most important issue in the micro machining zone, and we have seen that what are the different tool runout we are getting and what are the ways we can measure the tool runout also. So, let us discuss this thing further. So, we have seen that one of the reasons is the tool runout and another is the higher cutting forces related to the size. Now, if you see that we know that our specific cutting energy is very high in the micro machining zone, because we are cutting a material without any defect also. Sometimes we do not encounter any type of defect because the size is very small, and because of that our cutting edge radius and the chip thickness are also different way playing important role in this case. Now, we have seen that if you are doing a machining of a one material by two different tool, one is the micro tool and one is the conventional tool. If the material is hard, then it will actually hard for both the cases, right, whether you cut the micro cutting or do macro cutting. But problem is that in micro cutting, what is happening, the number of defects are very small, that we have discussed in the specific cutting energy part, and we are not consistently actually reducing the force when you are reducing the uncut chip thickness. So, after a certain level, force will be very high because of these material issues, and the cutting forces are larger and the liter cutter can exceed its bending limit. So, whenever you force your cutting tool into the workpiece without looking into this particular aspect, that is the cutting force to relative size, then what is happening, that you are actually bending the cutting tool. The material your tool is not able to force the material to cut, and because of that the material also plays some resistance to the cutting tool, and then it will actually cross the bending limit and tool will be broken directly. So, what is the thing, that we have to keep the tool deflection within the limit. So, whatever RPM and the feed rate you are selecting, so those things are actually synchronized, right. So, when you talk about the higher RPM, then only you can go with the higher feed rate, right, because in this case if the RPM is low, when RPM is low and higher feed rate, then there is a bending of the tool. Due to additional forces, right, because now your tool is here and this is the cutout material and you are moving in this direction. So, your moving direction is F is very high and your RPM is very low. So, in that time what is happening, the tool will be bent completely, because this tool is going down and down, but you are not removing the material. So, your tool will be something like this, sometimes it will be something like this, and once it crosses this particular bending limit, then there will be a fracture of the cutting tool. Right. Third one is the greater likelihood of the chip clogging. So, what is that, the micro mills are much more susceptible to the breakage due to chip clogging, because we know that when you are doing cutting operation, at the time there is a formation of chip, but in conventional machining what happened, that we are using a 2-flute cutter or the 4-flute cutter. The flutes are very important to navigate these chips completely out from the machining zone, but here we know that the chip space is the flute space is very small. So, at that time the chip will be clogged in between the workpiece and the cutting tool, and that creates the problem. That is, the available space for chips between the flute is smaller and the clogging tends to happen much more suddenly. So, you do not have some time also to understand that thing. By that time your feed rate is high, RPM is very high, you will suddenly get the clogging of the chip, and once the chip is clogged, then further movement of the chip is not possible. So, chips start accumulating at the same location, and because of that you will get the chip breakage. So, that is what is happening. So, because of that chip clogging, inefficient removal of the chip, and then you will get the then improper machining. Correct. So, in that way your tool is fully loaded, and once it is fully loaded, we know that suppose your tool is something like this is the 4 fluid cutter, then this whole thing is completely filled with the chips. Now, you are not able to remove that. Then what is happening, that when it is trying to cut the fresh material, then this particular chip will actually play a very important role in actually isolating this particular sharp edge with the cutting workpiece surface. So, in that case you will not get the efficient material removal. Right. Sometimes it is good to use HSS cutter which can bend more than the carbide without breaking, because now HSS, we know the carbide is very hard material and it do not have so much of bending strength. So, at that time if you use HSS cutter at a micron level, then there is a high chance that you can actually increase the bending up to a certain level, and if you can remove the clogging of the chip within that time, then you can actually continue cutting with the HSS cutting tool, then this part. So, this is sometime advantage, but you are actually sacrificing the hardness with selection of HSS. So, if the chips do clog, the cutter is likely to break within the relatively few rotations. That is obviously because now you do not have space to accommodate a fresh chip, and the fresh chip if it is not there, then everything is actually jammed in between the workpiece and the cutting tool. For harder material, what prefer that it is better to go with the 2 fluid micro cutting tool, because what is happening. So, this is the 2 fluid cutting tool. So, it has a 2 fluid. So, micro milling produces a large amount of chip than conventional milling, that is with respect to the size, and the fewer fluids will provide the larger gullet space. So, now you have a space this much, because when it is cutting the surface, now you can see this is the diameter and this much amount of space is available for actually evacuating this chip away from the machining zone, correct. So, this is the way you can do that thing, but there is a trade off also, right, because every time this is not the solution. Why it is like that? Because more fluids you can sure that there is always a fluid in the cut, right. So, this is the 4 fluid cutter. So, how this thing is better in some sense is, now you can see that when you are rotating the cutting, now if you see this is your this is your workpiece and you are going into that, and this is the rotational direction, right. And if you go with a high speed, what is happening, that in a one rotation only 2 places are there where your cutter is coming into contact. Remaining this particular portion, when it is touching, now if you see this is going continuously, right, it is not that intermittently. So, when it is going in continuously, there is some instant where this portion actually comes into contact with the workpiece. So, that is called the hammering vibration, right. Your cutting edge is not coming, because when there is a cutting edge is very sharp, and sharp edge can remove material efficiently. But here actually it is something like a hammering, that your workpiece, your tool is actually hammering the workpiece surface, and because of that, here when it is touching the surface, obviously material will not be removed, because there is no sharp edge or there is nothing which can remove the material. So, it is actually forcing the material inside, and by second instant your cutting edge is coming into contact. So, intermittently you will get a hammering effect in this particular case, but that can be minimized if you are using a 4 fluid cutter, right. So, what is happening in 4 fluid cutter, that when it rotates in one rotation, because now you can see that this is what is in your situation now. So, workpiece the tool workpiece is coming into contact at the 4 places where the sharpness is there. So, in one rotation you can get that you are making sure that your cutting, that means whatever your fluid that cutting edge is, that is coming into contact. So, that is opening only 2 times here. So, the hammering effect can be minimized, mostly it may not happen also, because when you are rotating at 1000, 50,000, 1 lakh RPM, you may not encounter this particular hammering action at this location, but it may happen at this location, because now you have to pass through this particular location which do not have any type of surface which can remove the material. So, by more fluid, what you are making sure that there is always a cutting edge which removes the material, but problem is that now you are end up with the less amount of space for the chip. So, chip clogging is issue here, but if you want to avoid the chip clogging, you have to reduce the number of fluid, but problem is the number of fluid reduced, then you will get the hammering action. So, here bending is high and here the chip clogging is high, right. So, again there is a compromise. Now, you have to see that for which particular application you go with the 2 fluid and which application you go with the more number of fluids. And fourth issue is the built up edge. Now, built up edge is really creating problem, because built up edge is much more likely on the micro cutter, because it too leads to the more force being required and more deflection, finally the breakage part. So, what is built up edge? That you get some material deposited onto the cutting edge of the workpiece material tool, and because of that your tool will consider as a more amount of radius. That means, whatever cutting edge radius of the cutting tool is there, by built up edge it will be further more, and because of that we know that if it becomes dull, whether by the wear also or by deposition of other material, your force requirement will be very high, because now you are not consistent with the uncut chip thickness to the cutting edge ratio, and then there is more deflection and there is a breakage at the final stage. So, what is the strategy? That means, when you are doing machining at the, better to go with the shallower depth, because you do not give lot of amount of depth. If you go more depth, then what is happen? The chip has to flow through all the fluids, and then it will create a problem at the later stage. And give the smaller step over. That means, once you want to cover more amount of surface. Now, consider that suppose this is the surface and this is your cutting tool. So, in a one go you are cutting this much amount of material, right. So, your cutting tool is coming like this, and once it is over, then you have to cover this part, then give a small step over, right. So, if you are giving a small step over, then what happens? Then the next step, suppose your cutting tool is here, then only this much amount of extra material is cutting in the next step. So, amount of material removal is, you will take more time, but you are making sure that you are not coming across the built up edge, because every time it is a compromise only. You cannot get everything right by setting all the parameters. So, somewhere you have to sacrifice. Here what we are sacrificing? We are sacrificing time, right. So, in this way what we are doing, the smaller step over will make sure that every cut has a less amount of material which is passing through the cutting tool. Shallower depth, then with diameter depth wise also you can go less. At that time you also make sure the amount of material which is coming out of the workpiece is less, and the fluid are enough to pass those material away from the machining zone. And other than that, you can actually use the mist coolant or the fluid coolant, but mostly in the micro machining mist coolant is preferred, because mist coolant will not create this space more messy, as well as the mist will make sure that when you are impinging with a high velocity or high pressure, at that time it is actually spreading the chips and whatever other dirts available which is away from the machining zone. So, that are the advantage, that mostly people go with the mist coolant, right. So, now finally the complete summary, that what is required for micro machining success. First thing is the accuracy required, because we have seen that if your machine has very high accuracy, but your feedback system has low accuracy, then your machine actually you are working with a low accuracy only. So, at least 10 times more than the feature size or the tolerance required. So, that is 10 times is everywhere, because we have seen the run out also in terms of 10 size, in the machine accuracy with respect to the feedback accuracy also 10 times or something. So, this is considered as some type of benchmark, but it is not same for every cases, but mostly people follow this particular benchmark, so that you can get the required things done very easily. Minimum run out, because that is, we have seen that this is creating lot of problem in the machining part. Most important for the micro tool lives, care for deflection in the cutting forces, because now we have seen that because of the run out, then chip clogging and the improper setting of the speed and feed, at that time you will get the deflection of the deflection of the cutting tool, and you will get a very high fluctuation of the cutting forces. and the micro tool will deflect much more easily. So, that is mostly this is HSS. So, it is bending little bit more, but if it is a carbide cutting tool, then it will be broken from some location wherever there is a high stress concentration, right. So, forces are 2 to 20 times greater than the macro machining the model machining model would per product. So, in the when you do force modeling, at that time you will encounter the forces are very high in the this particular, when you are talking about the workpiece, that particular zone. I mean, total force is very less, but if you consider the amount of material which is removing with respect to force, then it is very high. And always use the shortest possible tool to maximize the rigidity, right, because do not give the lot of overhanging, because sometimes what happens that suppose you have a this much amount of cutting tool length here available. So, hold it from this location, right. So, do not, because we know that if it is a length is less, then your bending will be less, right. So, if you see this thing and this thing, then there is a less bending in this will be less. So, if you give more and more overhanging portion, then there is a chance of a bending or it is a breakage of the cutting tool. So, you can actually maximize the rigidity by giving a less amount of tools length. Yeah. Care for chip load and the feed rates now, because we know the cutting edge radius is same as the chip rod. So, mostly we have seen that it will come across the negative rake angle and very narrow range of acceptable chip load before tool life, and outright breakage become the problem. So, when we know that how much is the amount of material you want to remove, then accordingly you have to select the feed rate, because feed rate will tell you that how quickly you are penetrating your work tool into the workpiece. If you do not have high speed, then actually you have to sacrifice the feed rate and finally the production rate completely. So, in this particular case, you have to make sure that you do a chip load calculation based on the feed rate and the speed what you are using, as well as the depth of cut also. High speed spindle is required, because only high speed spindle will make sure that your machining speed is high. The only way to increase the machining speed in this case, and allows the reasonable feed rate within the limitation of the tolerable chip load, because if you do not give a high speed, then you have a restriction on the feed rate, and if you have restriction on the feed rate, then you are restricting the total machining speed also, that you cannot actually operate the machining at the full capacity, and the production rate will be very low. Inspection is very important here, because for the most part you have a hard time using a micrometer to accurately measure those tiny parts by hand, because when you do micro machining or conventional machining, you can use micrometer, or you can use vernier caliper, or many things are there by which you can do the measurement, but here nothing is possible, because those parts are very small, and by putting this micrometer itself is a issue. So, you have to spend lot of money in the inspection system, the tool maker microscope, machine vision, lasers, 3D touch probes. So, these are the different instruments are available. Some of the instrument you can directly mount on the machine itself, so that you do not need to remove the workpiece also or the tool also. It will do measurement of all the things, that suppose you want to measure the dimension of the hole or something, then there are probes available. Some of the things are infrared probes also, some of the wired probes are also there, by which you do not remove the material, you do the measurement on the machine itself, because we know that once you remove the workpiece from the table, again putting it at the same location with the same accuracy is very problematic. So, it is better that you do everything within the machine also, machine only, by or let it be on the tool side or the workpiece side. So, that need the high all the things. So, here that is important. Touch probes are also, machine vision is available, because by which you are using some type of high magnification microscope, and you can actually monitor the machining operation also, and you can see that how the machining is being done. Another thing is the software. Now, how software is playing important role here, because what is happening that it is difficult to hear a cutter health when you are doing micro machining. So, when you are doing a machining with a high feed and high speed, at that time you have to select those parameters in such a way that your machine or your tool is able to bear those things, because now whatever operation we do, mostly we do by GNM code, and GNM code is mostly created by some type of third party softwares, by which you create a tool path and then give a feed rate and the speed data or all the things. So, if whatever software you are using, and if that software is not capable to give those particular things correctly, then what is happening, that a little tool deflection is happen, because your feed rate is very high, your speed selection is less. even though you have given everything to the software, but software has software does not have that capability to handle those things. So likewise, very little tool deflection at wrong moment will snap your cutter instantly. So we have seen the geographical error. Similar way, this is the error because of the wrong parameter setting, and that is the way you need a very high quality tool paths. So generating of tool path with a one particular feed rate and speed, that reads some type of high resolution or the high quality of the tool path, and that is possible by the software. And invest in software that will help you through the different type of issues. So you have to select the software also in such a way that it will provide some type of things which are very convenient to process this part. So let me stop this particular thing here, and let me show you one video here that how these tools are fabricated. Now this is the things which is fabricated by a grinding operation. Now see, these are the different tools available. Now you can see that this is the grinding wheel and this is the cutting tool. Now you can see how it is indexing and it is creating fluid onto the surface. And once you can see that these are the two different processes, right. So this is the one grinding wheel and this one the other one. So this is the coarse one, right. First the tool was coming here, that was shaping that, and this is the finer one. We have also seen same thing into the slide also, that how it is making the things. So now this is the animation by which you can see that how it is creating fluid onto the surface. And this is the final shape, whether you want a ball end cutter or you want end milling cutter, depending on that you can see the things here. Now once you create this thing, then you have actually using those tools in the machining process. And this is, you can see that this is showing the what is the tool run out, and this is the diameter of 500 micron, and you are cutting the this thing, and this is at high speed machining operation. That means you are using some high speed camera to see the things. It is now 300 micron cutting tool, and this is the 1000 image per second high speed camera, and now it is 100 micron end mill cutter, right. So in this way you can see that what are the different features you can create by different operations. This is the one thing. Yeah, so you need to spend some on the that also camera and all the things also, because once you create those pictures, then quickly you should have some system or by which you can measure the dimension and everything. So this is the vision system available by which you can do measurement of different features. Now you can see it can easily get this particular thing. See, it is creating this radius and everything. So micro inspection you can easily get this thing done, and this is the machining at a 4 lakh RPM. Now you can see that at which this RPM, that your spindle is rotating at a 4 lakh revolution per minute, and let us see that how it will do machining. So these are the different parameters. So workpiece is aluminum alloy, then work diameter is 300 micron tool diameter, spindle is one particular company spindle, then it has a 4 lakh RPM, and feed rate is 100 and 1270 millimeter per minute, and depth of cut is a 25 micron. Right. So this is the workpiece and this is the cutting tool, and this is showing in the real life. That means we are not using any type of high speed camera here. So feed rate is 50 inches per minute. Now you can see the way it is moving or it is doing cutting. So it is showing in the real time. So this is operating at a 4 lakh RPMs. So these are the different feed rate thing by which you can do study and see that which feed rate is showing you the better results here. And these are the different workpiece and different shapes which are cut by the different RPM settings. Ceramic is a 4.5 lakhs RPM, 3 lakh RPM, some other materials. Right. So, let me stop it here now, and we will continue new topics in the next class, that is more related to the micro factories. Thank you very much.